Electromagnetic waves. In this lecture, I'm going to show you how Maxwell's equations predict electromagnetic waves. Based on that argument, we will derive the wave equation from Maxwell's equations. Then we will solve the wave equation and discuss the solution a little bit. The main dissection of the wave equation and discussion of the various parameters, that will happen in later lectures. We'll just derive the solution and look at it a little bit. So first, the discussion about how Maxwell's equations predict waves. Let's remind ourselves what Maxwell's equations are. We have two curl equations, we have two divergence equations, and of course we have the constitutive relations. It turns out the divergence equations don't have much role in this discussion, and we can also take the constitutive relations, substitute them into the curl equations, and really just have two equations then that will describe and predict waves. So here we are with our curl equations after we've substituted in the constitutive relations so as to eliminate the D field and the B field. That is the electric flux density and the magnetic flux density. So if we look at this first curl equation, the curl of E equals minus j omega mu h. What does that mean? That means if we have an oscillating magnetic field, that will induce a circulating electric field around it. If we look at our other curl equation, this is telling us if we have an oscillating electric field, that will induce a circulating magnetic field around it. This is really the basis of how Maxwell's equations predict waves. A magnetic field induces an electric field. That electric field induces a magnetic field. That magnetic field induces another electric field, and this keeps repeating. So let's try to visualize this. Let's start with an oscillating electric field. We don't know what caused that, just for some reason there is an oscillating electric field. Well, we know from Maxwell's equations, an oscillating electric field will induce a circulating magnetic field. So now what we can do is ignore most of those oscillating magnetic fields. Let's just look at one of the magnetic fields oscillating on axis. So we focus on one of those. Well, we also know that an oscillating magnetic field will induce a circulating electric field. That comes from the other curl equation. At this point, we can just focus on one of the electric fields on axis, ignoring the other ones. And we know that an oscillating electric field will induce an oscillating magnetic field. Back to the first of the curl equations. Then we could focus on one of those magnetic fields on axis. That would induce a circulating electric field, and so on and so on. And so we also have a picture way now to describe how Maxwell's equations predict waves. Armed with that visualization, let's move on to deriving the wave equation. So here we are with our curl equations, and it makes sense if these two curl equations is what predicts waves, it makes sense that combining them is what we have to do to predict the wave equation, or to derive the wave equation. So one way we can derive the wave equation is to solve the first curl equation for the magnetic field. We can then take that expression for the magnetic field and substitute that into the second curl equation. Now we have a single equation just in terms of the electric field. So that really is the wave equation. Now we're going to work on that and simplify it, but that is the wave equation. It contains information from both curl equations, but just in terms of a single field quantity. The next thing we're going to do is take this 1 over j omega, and we can bring it to the outside of the curl operations because it's a constant. It's not a function of position. We can then take that j omega and bring it over to the other side of the equation. The j's will cancel to give us a -1. We'll end up with an omega squared. So this happens on the next slide. So that really is the final form of our wave equation for the electric field. And here we have an anisotropic permittivity and anisotropic permeability. And they can be inhomogeneous. They can be functions of position. So this really is the most general form of the wave equation. Yeah, but not very useful for paper. It's very difficult to solve. So you'll mostly see this just used in computer simulations when there's anisotropic materials or inhomogeneous materials. And in fact, if you're simulating something, there's almost always inhomogeneous materials because devices, by definition, have to have more than one type of material. Nothing useful happens when you only have one type of material. We really would like to bring this permeability to outside the curl operation so that we could bring it to the other side of equation, and that would simplify things down. But we can't do that because this curl operation has spatial derivatives in it, x, y, and z derivatives. So if the permeability is inhomogeneous, that is a function of position, and we can't bring it to the outside. So the only way we can simplify this form of the wave equation any further is if we assume the materials are homogeneous. And that is our next step. So now we're going to assume we're in linear, homogeneous, and isotropic media. And so, first of all, notice the brackets have disappeared from our material parameters. They are now scalar quantities and not tensors. Next, this permeability is a constant, and so it can come to the outside of the curl operation. Then we can bring it to the right-hand side of the equation and just end up with an omega squared mu epsilon on the right-hand side. However, on the left, now we have this double curl operation, and so we need to handle that. So there's a vector identity that we discussed way in the beginning of the course of how we can express this double curl operation as the gradient of a divergence minus a vector Laplacian. So let's apply that vector identity to our current wave equation where we have this double curl. So we replace the double curl with the gradient of the divergence minus the Laplacian. Then we rearrange terms a little bit. We leave this vector Laplacian on the left. We'll bring over the omega squared mu epsilon e term to the left and move this gradient of the divergence term over to the right. And let's give this some more thought. So we'll go to the divergence equation, which says the divergence of the D field is 0. However, our wave equation is in terms of E. So let's see what happens when we put our divergence equation in terms of E. Well, we have our constitutive relation that says D equals epsilon E. Now we've made another simplification. We said this is a homogeneous material. That means this epsilon is not a function of position. It's just a constant. It can come to the outside of that del operator. Now we can divide both sides by epsilon, and we get that the divergence of E must be 0. Well, that means the entire right-hand side of our wave equation vanishes and becomes 0. And we arrive at the final form of our wave equation for linear, homogeneous, isotropic materials. Well, that omega squared mu epsilon, maybe that's a little bit of a complicated term. Let's call omega squared mu epsilon, let's call that k squared. And this k is called the wave number, and this is something we'll discuss a lot more in future lectures. An alternative thing that you'll see is rather than define omega squared mu epsilon as k, define negative omega squared mu epsilon as a gamma. And this is called the complex propagation constant. So two different ways of doing this. that lets us express our wave equation one of two different ways. Now these wave equations look the same. The only difference is when we're using the wave number, we have a positive sign here. And when we're using the complex propagation constant, we have a negative. The solutions we get to this will also look the same, except when there's a positive sign here, we'll get complex exponentials. And when we solve it with the negative sign, we'll get just exponentials with real values in the exponent. Now let's talk about the solution. So here's our wave equation, and it contains this term E, which is a vector. So in Cartesian coordinates, it contains an x, a y, and a z component. So let's go ahead and expand that electric field in terms of its components in Cartesian coordinates. So we end up here. And we've expanded this E in its XYZ components and the second one in terms of its XYZ components. The next thing we'll do is we'll take this Laplacian operator and bring it inside the parenthesis and multiply each of those three terms. Likewise, we'll take this k squared and bring it into the parenthesis and multiply all three terms. So we've multiplied everything out. The next thing we'll do is we'll see that here's a component in the x direction and another component in the x direction. So we will group these two together. Likewise, we will group together the y components, and then we'll group together the z components. When we do that, we get this equation. Now, all of this has to equal 0. That means each individual component itself has to equal 0. That means we can take this single vector equation and write it as a set of 3 scalar equations. Now notice those equations all look the same, other than one has an EX, one has an EY, one has an EZ, but it's the same differential equation. That means it has the same solution, the same general solution. So we can just write our wave equation this way and not even really write a subscript here. We'll have to just sort of keep in mind that could be x, y, or z, but we can just solve this one equation and reuse that solution for each of these three equations. And this happens because we are in a linear, homogeneous, isotropic medium. So there's the final equation that we have to solve. So we could hand this off to a mathematician, and they may not even know what it is, but they could give us the solution, and then we could start analyzing it and giving it physical meaning. So if we did that, this is the solution that they would give us. And so now we can start to put physical meaning to the terms. If we look at that first term, we see a complex exponential, and you know what? That is the form of a plane wave that's propagating in the direction of k. K is called a wave vector. That's something we'll talk about in other lectures. R is vector position, and of course J is the square root of -1. And then our forward wave can have some kind of amplitude. And we write this positive superscript just to remember that this is the amplitude of the forward wave. Well, if we look at the second term, it looks almost the same, except there's a positive sign in the complex exponential. This term is a wave traveling in the backward direction. So it's sort of in the direction of k, but it's actually in the direction of -k. The backward wave can have a different amplitude than the forward wave, so we give it a different term, and it's different because it has the negative sign in the superscript to remind us this is the amplitude term for the backward wave. So we could do this same work for each of those three differential equations we had, one for the x component, one for the y, one for the z component. But as we said before, it has the same solution. So in fact, just by observation, we can write the solution for each of our vector components, EX, EY, and EZ, from the one solution we obtained on the previous slide. At this point, we can collect them back together to our vector E. And we'll put our solution for EX in the X direction, our solution for EY in the Y direction, and the solution for EZ in the EZ direction. When we do that, it looks like this. That resembles the solution for a single component. It has the same exponentials. The difference is these amplitude terms are now vector quantities. We still have the negative and positive superscripts. Those are different vector quantities for the forward and backward wave, but they are now vector quantities that have an x, y, and z component. And we'll also learn that this is the polarization of the forward wave, and this is the polarization and amplitude of the backward wave. So if we just look at one of the waves, let's just look at the forward wave and write it in its general form. So the overall electric field has a polarization vector, which has the amplitude and polarization information of the wave. And polarization is something that we will talk about later. And it's the alignment of the electric field. And we can see that just by how it's expressed in the electric field equation. And then this complex exponential that actually describes the oscillations and the wave and the direction the wave is going. So this is the frequency domain form, and it's usually preferred because it's easier to work with, but we can also write it in the time domain form. And so we have the polarization vector, but now our complex exponential, if we just look at the real part of that, now we have a cosine, and this omega t that we dropped because it was just implied by this phasor, we put this back in. So we have an omega t minus a k dot r. Again, where this k is our wave vector. Omega is the angular frequency. It's not the ordinary frequency. The omega is not the kilohertz, megahertz, gigahertz kind of number. This is an angular frequency in radians per second. So this omega term is really talking about how quickly this wave oscillates with respect to time. Then we multiply it by time. Looking at that interpretation, we can interpret these two terms. This wave number is describing how quickly the wave varies with space, and then we multiply it by the space term. So R is the vector position, vector E is the total electric field, polarization vector, angular frequency, time. Here's all of our terms. And by the way, the angular frequency is related to the normal frequency through omega equals 2 pi f. And the ordinary frequency, that's the cycles per second, the hertz, kilohertz, megahertz, gigahertz number. Now we derived the solution for the electric field, and we could ask, well, what about the magnetic field? We could do one of two things. We could go back and do everything all over again, derive a wave equation for the magnetic field and solve it and collect everything back together like we did. It turns out we would get the same exact solution, but we would have the polarization of the magnetic field. Well, rather than do that, we've already done this work. Why not just take this solution, plug that back into Maxwell's equations to find the magnetic field? So that's exactly what we'll do. And we refer back to Faraday's law, where we have the curl of E is minus j omega mu h. Well, we have an expression for E now. Let's put that expression in for E, do some math, and solve for H. So we put that expression in, we do our math and solve for H, and now we have a general expression to find H given the electric field parameters. Notice we have a K cross P. Remember the property of cross products. The vector that we get from the cross product is perpendicular to both of these quantities. That means the magnetic field, H, will be perpendicular to the direction of the wave and also perpendicular to the direction of E. And it's going to turn out when we talk about polarization that E, H, and the direction of the wave will all be at 90 degrees with respect to each other inside of LHI materials. Let's repeat this in terms of the complex propagation constant. So we had this original wave equation, and if we were to solve this in terms of the complex propagation constant, here is the answer we would get. This looks very, very similar to what we had before, except now we have a gamma sitting here instead of a K. And one other big difference, we do not have a J sitting outside of here. it turns out that imaginary J is still there, but it's built into this complex propagation constant. Not such a big deal mathematically, it's just something that we need to keep track of. So given that, and we just look at one of the waves, we can write our general expression for a plane wave this way. And there is a way that we can convert this to the time domain, but the complex propagation constant, always really being a complex number, that's not real convenient to do. So we'll handle it differently when we get there. Then the magnetic field, in terms of this complex propagation constant, derived the same way when we had K, ends up here. And so it turns out our gamma vector and K vector are related through this simple equation. It's just a J sitting here. So really not a big deal, and I'm giving you this more just so that when you're reading the literature you can see gamma and K. I tend to like to always use K. I really only use gamma sometimes in some simulations where it's more convenient, or if I'm deriving something and I'm trying to stay consistent with another derivation that I'm working off of. But my own personal work, I really just usually work with K. So we derived our solution. Let's think about what waves actually look like. So what we're looking at here is a very traditional visualization of a wave. I think this is a good way to visualize waves. It's one of the best that I can come up with, but it's also very misleading. This tends to imply that the wave is confined to be on the z-axis, and that's not true. This wave, if we're talking about a plane wave, it is of infinite extent in the x and y directions. So make no mistake about that. It's just that it becomes more cumbersome to draw. And in fact, I try that on the next slide, we'll see. So that part's unrealistic. Another thing that's unrealistic is the magnitude of the magnetic field here. Here it looks like it's, I don't know, maybe a fifth of the amplitude of the electric field component. And in reality, the electric and magnetic fields, they're related through this material parameter called the impedance. And I'm jumping ahead. We'll talk about this later. And the impedance of a vacuum is around 377 ohms. So the electric and magnetic fields are really 3 orders of magnitude different. That really can't be drawn. If I were to draw this to scale, we wouldn't even see the magnetic field. So I had to artificially amplify it just so that we would see it, but I still drew it a lot smaller than the electric field, I don't know, to help us visualize that. Now that really does not mean that that magnetic field is weaker than the electric field. It's just really the units that we've chosen for electric and magnetic fields. It's a convention that somehow the world has converged to. So that's how we're visualizing our wave. Notice the electric and magnetic fields, they're perpendicular to each other. They're also perpendicular to the direction the wave is going. Okay, so this is a bad visualization in that it doesn't really show the extent of the wave. Let's go to the next slide. In terms of technical accuracy, this is probably a better visualization because it shows that the wave is really distributed throughout. And in fact, it continues off to infinity in the x and y directions. But this is kind of crazy to really visualize what's happening. Yeah, we can kind of see it, but when we're looking at the electric and magnetic fields everywhere, it's very jumbled and hard to see. And that's why we don't see visualizations like this. In fact, that's a problem that I'm thinking about right now. How do we visualize an electromagnetic wave so you can see the oscillation, so that you can see which direction it's going, you can get its amplitude, you can see its polarization, and all the materials that it might be interacting with? That is a really tough visualization problem, and I don't know how to solve that yet. In my head, I tend to visualize the electromagnetic fields like cloud or fog, but that doesn't convey the vector nature of the electromagnetic field. So I don't really have a good answer to this, other than what we saw on the previous slide is probably the best because it's simple. It's just, it tends to imply things that aren't necessarily physically accurate. So that's it for this lecture. I hope it was helpful.